thank you for the introduction. Can you hear me? Also, thank you for being here. That means that either you are very fast eaters or you even fasted to come here on time. So, as I said, I work in machine learning for healthcare at the City of Hope National Medical Center, which is a cancer center in Duarte, east of Pasadena. It was recently rated as #1 cancer center in the West. The person in this picture is Peter Lee, who is the director of research at Microsoft. And last week, he gave a keynote talk at KDD 2019, which is probably the #1 conference in data science, and he talked about digital health and digital health at Microsoft. And one of the themes of his talk was about the needs for data science and machine learning in healthcare and how healthcare could benefit from data science and machine learning. And this is a recurring theme if you attend a lot of workshops or talks or conferences about machine learning in healthcare. This is a recurring theme. On the other hand, in different industries, like advertisement, you don't hear this type of theme. So this tells you that there is still a lot of road to be done for machine learning in healthcare. It's not as advanced as in other fields. One of the side effects of this is that the best practices are not very well established yet. For example, this is a slide from the 2018 conference on machine learning for healthcare, where in the final panel, some experts were discussing about drafting guidelines for best practices for the field of machine learning in healthcare. So there are various motivations for applying machine learning in healthcare. I mean, most of them are obvious. The main one boils down to the fact that there's a lot of information about patients, and on the other hand, clinicians don't have enough time to process all this information. So a physician at the talk last week was saying that physicians maybe barely have time to go in the past history of the patient and pull one note, while maybe it'd be useful to go through 10 notes of in the past history of the patient before maybe making a diagnosis. And another problem, another bottleneck is the physician actually have to spend a lot of their time just entering information about the system, entering notes about patients and other type of data, which is also time consuming, and they don't enjoy doing this very much. Another aspect is in a lot of scenarios there are a lot of false alerts, because those are due maybe to scoring systems that are not very well designed, and so there are a lot of false alarms that get neglected, and once in a while actually the false alarm will be true, and then problems happen. So in this talk, I'm gonna give you first an introduction about the electronic health record, which is a type of data I work on a daily basis, and then I look at some aspects where I notice or even experience myself some pitfalls. And in particular, I'm going to talk about core definition, data quality, how to best explain your training and testing set. I will also talk about performance metrics. And in the end, if there is time, I'll also talk a little bit about survival analysis. So most of these topics are concerned, if you have in mind the typical pipeline, machine learning pipeline, where you have extracting the data, preparing the data, extracting the features, etc., etc. Most of this talk is going to be about aspects related to data preparation. This is based on my experience, where I notice most of the pitfall happening. One other thing I do besides being a data scientist at the cancer center is also I review papers submitted to conference in applied machine learning for healthcare or journals, and so sometimes I see some recurring mistakes. So the electronic health records is a collection of all the data about the patient, and consists of in laboratory tests, vitals, diagnosis, medications, also other type of information like X-rays, possibly CT scans, electrocardiograms, notes. So this is a very heterogeneous set of data. We have multidimensional time series that can represent a lot of these type of data, like for example for lab tests, vitals, We have text, we have medical codes that also can be seen as a form of text with more constraints, smaller vocabularies. We have notes, of course, that's also, for example, of free text. And also, we have bidimensional, three-dimensional images, time series, for example, for electrocardiograms. The time is one of the key aspects of EHR data. Here, in this simplified representation, this axis is going to represent time. And we represent the information of 3 patients, and each dot corresponds to an event. Could be a lab, could be a vital taken, could be a note written, and some other type of events that you see in the previous slide. And so the temporal resolution varies a lot. If you have an ICU patient, it can be as refined as minutes, so we maybe monitor the patient constantly. For hospital patients, it's more coarse, maybe in the order hours, and then also you can have the case of outpatients, and maybe you come and see a doctor every 2-3 months, and then are going to continue the treatment at home, so where this temporal scale is in the order of weeks. This is some events. This slide shows some events that hospitals would like to predict from EHR data. Those are we'll say standard task for machine learning in healthcare. So unplanned 30-day readmission, the length of stay, the mortality means whether, for example, the patient is going to be alive or dead within a certain period of time, sepsis, ICU admissions, surgical complication. And for example, for the reason for wanting to predict unplanned 30-day remission length of stay is to increase the capacity of the hospitals. Mortality, for example, at the cancer center, for cancer patients, it's quite critical to take decisions, for example, whether subject the patients to some clinical trials that can save the life of the patient, but on the other hand, they're also high risk. So in these cases, for example, they would like to subject the patient when there's maybe 6 months life expectation, not to risk to kill the patient while there may be alternate treatments that are less risky than clinical trials. So of course, if they start too late, then there's no hope anymore. For simplicity, in this talk, we only consider a case of binary prediction task. So a classifier is going to either give a 0 or 1, or a score that ranges between 0 and 1. And for example, with a score close to 1, in the case of 30-day remission, would mean that there's a high risk of remission within 30 days. And in general, when there's a binary classification, there is always a trade-off between falsely detected and missed targets. So I'll talk briefly about cohort definition. So in this context, a cohort is a set of individuals with experience, with a particular experience during a certain period of time. So in our case, for example, if you want to study apply machine learning to the problem of predicting surgical complication, well, the first step we want to do is pull from a database the records from a set of patients who had at least a surgery within a certain period of time. So once we pick a subset of patients, let's suppose we pick these 3 patients over here. The next step is we have all their past records. The next step is to pick some prediction times in the past. And we discard the data posterior to the time, to this prediction time. So we want our model to make prediction at this time, at this particular time, based on the past data of the patient that could be, for example, limited, for example, to 6 months. And this is exactly, so we show this prediction time, this case of this prediction time, where we discard all the data after the prediction time, because we don't want to use virtually data from the future in general. Let's talk a little bit about data quality. For the people who came late, now we are talking about issues related to data quality in the electronic health record. So this type of data are challenging. I would have used the word messy in many different ways. Let's see some examples. For example, for lab results, this is some quite common non-numerical entries. I mean, me as an electrical engineer so naive in healthcare, I would expect for lab results the result to be either numbers or at most categorical variables. But in a lot of cases, we have something like literally the lab value is greater than 60 or is smaller than 2 and written as a string. And so this is, there requires a little bit more steps to clean the data. And another example I find interesting is date of death. I talked before about mortality prediction is one of the tasks of interest. So I look at discrepancy in the date of death reported by our internal records and date of death reported by Social Security Administration, and for a subset of patients who had the records in both those databases. And so for about 5% of them, I found discrepancies. Most of them, for example, we have a lot of discrepancy, 1 day error, so it's not too bad. Then increasingly, maybe 2 days, 3 days, etc. This is on the vertex, we have the number of errors, and the x-axis is the number of days. And then again, we have a relative peak at 2 months. And interesting, also a relative peak at about 1 year. So, and then you see is a very long tail distribution where we can have the errors for different values of days. Distinctions that is important to make here, and sometimes people confuse the two, are anomalies versus outliers. This is a recent tweet that I saw in my Twitter feed. And sometimes, as is mentioned, people use interchangeably anomalies versus outliers, but they're actually different, and also need to be treated differently when cleaning the data. So an outlier is a legitimate data point of a certain distribution that is far from the center of this distribution. On the other hand, the anomaly is an illegitimate data point that has been generated from a different process, from the main process generating the distribution. And so in most cases, one needs domain knowledge to differentiate between outliers and anomalies. Let's look at one example. The albumin level in blood is a type of lab test used a lot, at least for cancer patients, but I think also for a lot of other type of patients. The normal range is between 3.4 and 5.4 grams per deciliter. And in this particular cohort that observed, we have a mean of 3.5 and a standard deviation of 0.65. So for example, suppose we have an albumin level of -1. In your opinion, is that an anomaly or an outlier? Or anomaly, okay. Yes, well, this is trivially an anomaly because we are measuring a concentration, so it should be a strictly positive value. So -1 is negative, so it's trivially an anomaly. Let's look at this other value, 1. So 1 is like about 4 standard deviation away from the mean. Is this an anomaly or an outlier? Outlier. So this is possibly outlier. I said possibly because suppose we have all the other labs of the patient taken around this time that says that the patient is in normal condition, then maybe that 1 could be the result of a mistake that could be an anomaly in that case. Otherwise, we may assume this is an outlier, this is clinically relevant, and so we cannot treat this as a missing value. Another point where I see pitfalls is in a training and testing split. This is a tweet from Zachary Lipton, who is a professor at CMU and works very active in the area of machine learning for healthcare. And he outlines that the test set must be independent. Let's see what does it mean. So in general, a guideline is when we are evaluating a machine learning model, we want to evaluate the machine learning model on the ability to make prediction of new and unseen data. Of course, our data are all from the past, but we need to pretend that these data are unseen. And so an important step to make is split training and test based on temporal criteria. So in particular, we don't want any records in a training set as after prediction dates in the test set, but because that would mean to virtually using data for the future in evaluating our model. So for example, a random split of training and test in the case of healthcare data would probably lead to excessively good performances. Another possible pitfalls in having records across training and testing that belongs to the same patients. Also, if possible, this should be avoided. And another topic of this talk is about performance metrics. And again, this is by reviewing papers written by peers and submitted to conference or journal, I see errors in the, poor practices in the performance metrics a lot. So in generally, to give this information background, we are, as I mentioned at the beginning of the talk, we are looking at binary classification problem, and in healthcare, most of the binary classification problems are very unbalanced. So because we always want to predict an adverse events, and luckily the adverse events are more rare than the non-adverse events. So for example, we have about, in many hospitals, the percentage of unplanned 30-day readmissions around 15%. The case of sepsis is less than 10%. If you look at 30-day mortality, it's less than 1%. So those are all quite unbalanced data sets. And in general, if you look at the types of performance metrics, we are metrics that give the overall performance about the model and measuring trade-offs. For example, the receiving operating characteristics or the precision recall curve. And on the other hand, we have metrics that give the measure the error rates at specific decision points. So for example, look at the false positive, false negative, precision recall, F1 score, accuracy. In general, the first class of metric is good to give an overall characterization of the global performance of the model. The second class of metrics can be useful. Not all the metrics in the second class, but some of the metrics in the second class can be useful for example, to give clinician a concrete interpretation of performance of the model. If I tell a clinician that the AUC 0.9, it's maybe it's not very informative, but if I tell a clinician that given a precision of 90%, the recall is 10%, then gives a concrete idea of the rate of false positive of the model and how it's going to work in the clinical practice. So this is this is a beginner mistake. For example, I took a very unbalanced problem, so you definitely don't want to use accuracy for these problems because that is completely insensitive to unbalanced data set. And so for example, in the case of a model where we have a target class of only 5%, well, we could have a model that predict the negative class all the time. This could be completely useless and negative, and this model will lead to 95% accuracy. Another less intuitive error is to just rely solely on the area under the curve of the precision of the ROC, the receiving operating characteristics. This metric is actually also somehow misleading for unbalanced data set. And so we may have the case, for example, of a model with an AUC of 0.8, which is considered good, or even 0.9, but at the same time, if the data set is very unbalanced, this actual model may be not good at all in the clinical practice. I'm going to show more. There's also a paper about this that was published in 2015, where they recommend to use a precision recall plot, at least together with the ROC. This is an example from a paper of Andrew Eng and Anand Avati. They study mortality prediction for general hospital population. And we have two sets of tasks. One case they study 1 year mortality, and another case a 5-year mortality. So intuitively, the percentage of patients who are going to die 5 years from now is higher than the percentage of patients going to die 1 year from now, right? The longer the time difference, bring the time to infinite, everybody is going to be deceased. So the second task, the task on the left, is less unbalanced than the first one. But we see on the first one we have the model achieve an AUC for the ROC of 0.94, while only slightly below for the second one. So one simplistic conclusion would be to think, okay, the predicting 1 year mortality is actually easier than predicting 5 year mortality because the IUC is higher. But on the other hand, if you look at the precision recall curve and the error on the precision recall curve, then we see that the error for the precision recall curve for the first 1 year mortality is actually around 0.5, and is actually lower than the error for the under precision recall curve of the second model. So this shows that, for example, for this case, the precision recall curve gives a more realistic assessment about the performance of the model. So in general, a good guideline is to have, I would say, include both receiver operating characteristic curves and precision recall curve, and then also pick a metric from at the clinical meaningful decision point. For example, we want to see the recall at 90% precision. 90% precision means very low rate of false alarms, and a lot of healthcare application we want. It's important to have fewer false alarms, even if we sacrifice recall. Another good lines is to have a comparison with a known benchmark. So for example, this is another paper, Andrew Eng, which is a good example of good practice in picking metrics, and it's about improving palliative care with deep learning for, again, applied to mortality prediction. So for benchmarks, I saw some funny things happening, and it seems like several people in the field follow this tip from Big Data Borat. So maybe so yeah, easiest way to look for a good benchmark is to change benchmark. So this, for example, is a paper by a team from Google, Stanford University, and Chicago University, I think. And it was published on Nature, which is one of the highest impact journals last year. And it talks about application of deep learning of several healthcare problems based on AHR data. And in the main paper, if you download the PDF, you only see the performance of maybe the model on 6 different tasks for 2 different hospitals without any benchmark. But then if you look online on a Nature website, there's a link to some supplemental material. And in the supplemental material, the authors perform a comparison between deep learning, the approach they presented, and a simple logistic regression method. And one of the things that stands out is the deep learning only gains 1 or 2% in performance with respect to logistic regression. So this is another hint that in general, I mean, not based on this paper, but also based on results from other researchers, deep learning is very powerful in images or text, but if applied to the EHR data in general, which is heterogeneous, correspond also structured data, is not so powerful, and possibly could even be worse than gradient boosted trees. So this time. So another kind of funny example from an undisclosed vendor that shows the comparison with the benchmark. So blue is, true positive, false positive. Blue is the benchmark, orange is the performance of the vendor. If we scale the plot a little bit, I reproduced the original plot from the vendor with the original scales. If I rescale the plot from 0 to 100, then you see that in this case the performance with respect to the benchmark, yes, it is better, but not so much better. So sometimes especially vendors, they play also with the scales of the plots. And so final plot of this talk is about, I'll talk a bit about survival analysis. which is also can be a tool to assess whether you've done something wrong in preparing your data. As I mentioned before, so let's suppose that these plots represent EHR of some patients, where this is at the time axis, and this is some events like labs taken or lab results reported, notes written, vitals, etc. for the patients, different scales. So I said before, we have this record, we pick some prediction times and our model is gonna attempt to predict some outcomes, for example, mortality or surgical complication at this time based on these past records. It's very critical how the prediction time are taken, right? Because I could, for example, for this patient, I could take a prediction time on any of these points, assuming there are past records available to eventually extract features and train a model. So once we pick a prediction time, we can define a time to event. So for example, if we go back here and we assume that this is the last available record, and maybe when we have a square at the end instead of the dot, there's an outcome, like for example, I don't know, a surgical complication or death. Then we can compute the time between this prediction time and the time to event. For example, the time to death, or the time, in this case, for a patient we don't know the date of death, will call censoring time. So we have all these intervals for every patient in our cohort, and we can plot some survival curve where we look at the distribution of this time to events, where we have a different curve for the patient of the positive class. In this case, in this example, we consider death as the event we want to predict. So we have a red curve for the cis patient, a green curve for the alive patients. And we see, for example, here we have about, let's say, how to interpret this curve. Let's say at this point, we have about maybe 20% of the patient will die within 30 days from prediction date. And if you look at these points, we will have that within 1,700 days, all the patients in the disease cohort will be dead within 17 from the prediction date we picked. So given a set of prediction date, we can plot different survival curves. And so we show this example where this one, especially we focus on the survival curve for the disease population. We have the curve on the top left will decrease very rapidly, and this one decreases less rapidly among the three. And if we compare this curve with some curve we plot from past records of the patients, so for example, we look at the specific data in the past records, we look at patients who died given the date within 30 days, we see that actually the real curve are not as, they don't decrease as sharply as the curve we have on these. And so that means that in all these past survival curves, in particular for this one, we overestimate the percentage of patients, for example, that die within a certain time frame. And this also means that when we run a model, a binary classification, where on one hand we have alive patients, on the other hand we try to predict deceased patients, then we have a large percentage of patients with disease were very close to death in the way we pick the date of death, and we risk to overestimate the performance of the model. Because the model is compared within patients that they live at least 1 year, versus patients who died in 30 days. So they were in very critical conditions. So some final remarks, tips that I can give based on this talk. So outliers should not be treated like anomalies. You want to split the training and testing set or the cross-validation and testing set based on temporal criteria. The receive and operating characteristic curve can be misleading where the data sets are very unbalanced. So the precision record curve in the case of healthcare data or very, very unbalanced data in general is more reliable, often more useful than ROC. But ROC is also useful too, so you want to maybe use both. It's important to compare with a meaningful benchmark. And also if the survival curves are unrealistic, as I showed in the previous case, there's a risk of overestimating the performance of the model. This is the end of my talk. If you have any questions. Hi. There's a question. Is there a microphone for? Ask the question or repeat it.
Yes, I'm very curious about why the deep learning is just a little bit higher than the logistic regression.
Oh, in that paper, you're talking about.
Especially in our pharmaceutical industry, why it's just a little bit better.
So you're asking, your question is why the performance of deep learning is only slightly better than logistic regression? That's a very good question. In general, the rule of thumb is the more unstructured the data, for example, images, you can really explain an image with a table, right, or text. The better the performance of deep learning models versus traditional machine learning models like logistic regression or boosted trees. On the other hand, if you go towards structured data, then it's the opposite. You have boosted trees and logistic regression who actually, especially boosted trees, that perform better than deep learning. So in the case of healthcare data, you have a mix. If I go back in the presentation. Okay, I went too far. Yeah, you have a mix of a lot of type of data, and some of these data are actually better represented as structured, even though there are also unstructured components like the nodes. And so overall, that would be my intuition of why, for example, deep learning doesn't gain much.
So is it also because for healthcare data, we may have very high dimension, or we are lack of the?
Not necessarily, because, for example, for also nodes, text is definitely very highly dimensional. Suppose you have a vocabulary of 10,000 words. It means that virtually your node could be represented, if you do any other simplification, if you want to use all the words in the dictionary, will be represented with a 10,000 dimensional array matrix. So 10,000 column matrix. So high dimensionality is not the reason. It's more probably has to do with the fact that some of the data are actually structured. Thank you. Hi? Yes?
Hi. I think there's a lot of interest in machine learning applications here. And I was wondering whether you can speak about what's the state of using this type of models in a hospital or real-time patients, and what are the challenges that are rolling out?
Yeah, that's a good question. So I was making comparison before with other industries, and for some other industries, and some other problem, you see industry papers. For example, for Google, Airbnb, they talk about, okay, we apply this to spam detection, and this is the performance. I haven't seen. I saw a lot of paper on retrospective studies, and I've seen very limited amount of work on studies that evaluate the application of machine learning in healthcare. I know that some hospitals are using machine learning, but at the same time, I don't know. I haven't found any publication that tells how machine learning is going into those hospitals. So hopefully, maybe in the next couple of years, we'll have more results in these cases. So because I don't. Yes. Yes, because sometimes the model, that would be a case, for example, if you study the problem of 30-day readmission and you want to limit your record as just the event of admission in the hospital and stay in the hospital. So you can have a patient with multiple admissions, so you can have multiple records for these patients. If you put, let's say, some of these records in the training set and some of the records in the test set, the model could also learn not just to predict 30-day remission, but maybe just recognizing a certain type of patient. So for example, if you have, let's make a simplified example. We have a lot of demographics data about the patients and not so much data, not so many clinical data. The model will definitely learn how to recognize patients based on demographics data. And then if some patients are more subject to 30-day remission than some others, the model will still have some performance that seems good, but we'll just be able to recognize the patients based on the demographics rather than actually predicting 30-day remission or based on unseen data. So
in the real world, you're going to see frequent readmissions. I mean, if you deal with the data,
yes.
on a daily basis. I mean, I run large, like really large.
Yes, in the real world, let's say, you want to maybe be more rigorous when you do your retrospective analysis. In the real world, yes, you can have the cases where maybe my training data, because I have an admission in the past, can be also used to predict my real world events. But if I do this just based on my retrospective studies, then maybe, if possible, I would avoid this case. I would constrain the test set not to have, or the training set not to have records of patients who appear in the test set.
All right. Due to time constraints, Mr. Lorenzo is only going to take one more question, please.
Yeah. Hi. So you mentioned about the unbalanced data and the performance metrics, like this is what we call right? But I was wondering, before you run the models itself, right? Are there any data transformation methods? Like, can you reform the data into different, like a different variable from the variables you already have?
So you're suggesting, can I make the data more balanced?
Yeah.
Okay.
Are there any ways of making the data more balanced?
Yes, I can make the data more balanced in the training set, but on the other hand, I want my test set to be as realistic as possible, because I cannot make the data balanced in reality, right? In reality, maybe we have 5% of patients who get sepsis, and so the model must be able to perform in that scenario. So in my training set, I can definitely, if I think that I can help or can test, I can make experiments and maybe make the training set more balanced. But on the other hand, I want the test set to be as realistic as possible as a guideline.
All right, thank you guys. That was the last question. Again, thank you, Mr. Lorenzo, on behalf of DataCon LA 2019. And as a token of appreciation, we'd like to present you with this award and shot glass.
Oh, thank you.